If we forget for a second about the data collection process and we just assume that you have a data set, clearly changing that data set is going to change model predictions in some way. And so what we were asking is, can we, without actually thinking about the very mechanistic details of the learning algorithm itself, can we sort of black box that away and think of machine learning as just a map directly from training data set to prediction?
The Brave Search API brings affordable developer access to an independent index of over 20 billion web pages. Well, it's built from scratch without big tech biases, powered by real anonymized human page visits to filter out data and refreshed daily with tens of millions of new pages. Perfect for AI model training and retrieval augmented generation. Whether you're working on language models or information retrieval systems, Brave offers representative datasets and up-to-date information affordably. We'll get started with 2,000 free queries monthly at brave.com/API.
Cool. Andrew, it's an honor to have you on MLST. I've been a fan for years now. What's your bio? What's your background?
It's an honor to be here. So my name is Andrew. I'm a sixth-year PhD student at MIT. I'm advised by Alexander Modry and Kostas Daskalakis, hopefully graduating soon. I work a lot on robustness and reliability with a focus on sort of looking at the entire machine learning pipeline, from how we collect data to how we make it into data sets to what learning algorithms we use, and really trying to take a step back and look at the entire pipeline to answer questions about robustness and reliability.
Yeah, and that's really interesting because I think a lot of people, they put machine learning models into production and then they see all sorts of problems coming up. So we need to have a holistic approach rather than just looking at the individual components.
Yeah, absolutely. I think a big goal of my work is what I'd call predictability of machine learning systems. So really whether we can understand the principles behind why they work well enough that when we put them into production, we understand both when they're going to work and when they're not going to work, and also ideally why.
And what are your broader interests? I mean, how did you get to where you are today?
Yeah, so I started at MIT in 2015. Towards the end of my undergrad, I got really interested in this phenomenon of adversarial examples, just doing undergrad research with a couple of my friends. We worked on a couple of papers together and just got really excited about the field. And I sort of, into my PhD work, continued that interest for a while, working on both, developing attacks, but also trying to start an understanding of why these things even arise. And I think, gradually I can explain the whole path, but gradually that brought me along to this conclusion that we really need to understand the interaction between, training data and models, and trying to get at some core of why machine learning works the way it does.
So we're going to come back to adversarial examples, but just to give the audience a taster, what are adversarial examples?
Yeah, so an adversarial example is just a very small perturbation to a natural input, so that a machine learning model doing inference or behaving on that input misbehaves. And so in the context of images, that could be changing a couple of pixels so that a classifier misclassifies the image. There's been recent work on this in the context of language, where now you're trying to append a very small suffix or prefix to your prompt so that the language model does some unintended behavior. But broadly speaking, it's about slightly changing inputs to make machine learning models misbehave.
Very cool. And when we look at the entire predictive architecture, how do you kind of sketch out that structure?
Yeah, so I think about it in, at least 4 or 5 different steps. I think there's a data collection step, which is really, very modality dependent, but you can think of it as where are you even getting data from? We have to choose, for example, to get ImageNet from Flickr. Or for language data, we have to choose what kind of crawler are we going to build? Are we going to respect robots.txt? Are we going to try to generate synthetic data? And so I call that the data collection process almost. And then once you've done that, you sort of have to decide how you're going to package this into a data set. And so, for image classification, that's a question of which data are you going to include and how are you going to label it? For language modeling, you also have to decide which data you're going to include, what sort of data cleaning you're going to do and stuff like that. And then after you've done that, you have a data set, and that data set gets fed into a learning algorithm. And you can think of a learning algorithm as anything that takes in a data set and outputs a machine learning model. And so that encapsulates everything, hyperparameters, hyperparameter tuning, architecture search, whatever you're doing to get your machine learning model is included in that learning algorithm. And then even after you've done that, there's this step that I think, maybe not so much anymore, but often used to get overlooked, which is how you actually deploy this machine learning system, the machine learning model. I think, increasingly machine learning models are deployed into contexts where they're dealing with humans. And so you inevitably run into questions like, what are adversaries going to be able to do with this model? But also, like, what are normal behaving users going to do with this model? And I think there are, tons of interesting and funny failure modes of, not thinking about the last step in this pipeline over the last couple of years.
Yeah, and reliability engineering in general, it's really interesting because it's a moving target, right? It's not something that you can ever solve because the system is non-stationary. People are adversarially, attacking your system in a myriad of different ways. So how does that actually work, in a production setting?
Yeah, absolutely. And I mean, also the system itself is changing and getting better, and you're constantly, upgrading or making your model bigger. And so I think it's a very open question what the right way to do it is. I think the way that I'm partial to is to try to understand or distill, some general principles that underlie the behavior of all machine learning models, or all machine learning models in a broad class. And I think, that's a very ambitious goal, and it's unclear if it's even possible. But I think increasingly it's been getting a lot of attention, and I think that's good.
Very cool. So we should go to your data modeling paper first. So I think you wrote this about 2 years ago, and you were studying essentially how algorithms combine together with data to yield model predictions. Can you kind of explain that paper?
Yeah, absolutely. So the idea is that I just talked about this pipeline. If we forget for a second about the data collection process and we just assume that you have a data set, clearly changing that data set is going to change model predictions in some way. And so what we were asking is, can we, without actually thinking about the very mechanistic details of the learning algorithm itself, can we sort of black box that away and think of machine learning as just a map directly from training data set to prediction? And so what data modeling looks like is you hold, a single prediction fixed. So let's say you pick your favorite image in the test set, and you're just interested in studying your model's prediction on that specific test example. Your goal in data modeling is to predict, as a function of which training data you train on, how your model is going to behave on that test example. And so what that looks like is basically a surrogate supervised learning problem where your inputs are data sets and your outputs are model behavior on a specific test example.
Yeah, so there are some similar things that have been done before. I mean, there was I think influence functions and Shapley values and so on. How does it kind of relate to those?
Yeah, absolutely. I think it's useful to maybe think even before the era of deep learning, there was this field of influence functions and statistics that basically came from this need of being able to estimate parameters had you weighted your data differently. So people had these what they called M estimation tasks, and they wanted to know if I dropped out some of the samples, or mostly it was a theoretical tool, but if you dropped out some of the samples, how would your estimator change? And so conditioned on a bunch of pretty strict assumptions in statistics, we came up with really rigorous tools with theoretical guarantees for answering exactly that kind of question, which looks a lot like the data modeling task actually. And so there was this brilliant paper in 2017 from Peng-Wei Ko and Percy Liang at Stanford that basically took these statistical tools and applied them directly to deep neural networks and found that it doesn't actually work so bad, even though in deep neural networks none of the assumptions that the stats people cared about were true. And so that was a huge first step. After that paper came out, there were a couple of follow-up papers, both supporting and building on the estimator, and also a couple of ones in parallel that showed that it wasn't reliable. For example, when networks got too deep, or when networks got too wide, or under different hyperparameters. And so out of this was sort of born this field that's I think now referred to as data attribution. And so shameless plug, we gave a tutorial on data attribution earlier at the conference on Monday, and the notes are available online. But I think that it's a really good way to answer the question you were asking about how do all these things fit together. And I think broadly, you can think of data modeling as sort of formalizing the goal of what you might call predictive data attribution. So really your goal is just, you give me a training data set, I predict what your model is going to do. And so an influence function is one way of doing that. There are a variety of other ways of doing that. And I think the point of the data modeling work was to show that this goal was even actually extremely possible. Because prior to, I think, the data modeling work, there wasn't really convincing evidence that this was even a possible thing to do for deep neural networks. The Shapley value stuff is also really interesting. It turns out that there are a lot more connections than we realized, or than I think anyone realized when we were writing the paper. But broadly, I think the sort of overarching way you can distinguish them is that there's this line of work that's most interested in assigning credit to training examples. So when you're estimating Shapley values, your actual goal is to sort of understand what is this example's fair share of a model prediction for each example in your training set. So you might, have some target image of a dog or something, and you want to figure out like how important was each dog in my training set for my model's output on this dog. Whereas in data modeling, the instantiation we gave in the paper is linear. And so as a result, the coefficients end up looking a lot like, estimating the contribution of different training examples. But the goal is actually much broader than that. What we're really trying to build is a generic estimator that just maps from data sets to, predictions.
Very interesting. I wonder, how is it related to machine teaching? I mean, I found out about machine teaching a few years ago. And as I understand it, it's a way to kind of find the minimal data set. So some kind of meta process where we carve down the data set to find the minimum size one that will still do well on the problem.
Yeah, absolutely. I think, machine teaching, I've heard data set distillation as well.
Oh, yeah.
And, a couple of those core set finding, I think, is another name. But I think there are a variety of these applications where what we really care about is like narrowing down the data or like preserving the information that's present in the data set while cutting down on the number of data points. And so I think it's a really interesting complementary goal to data modeling, or almost one that could benefit from data models being used, because, and I'm sure we'll talk about this later, but I think that where I'm most excited about things like data models being used is in tasks where you can write down an optimization function in terms of your training data. So if you can really write down like, I want to minimize over my training set some function of model predictions. Anything that looks like that, I think, just plugging in what something like data models predicts will happen can be a really powerful primitive. And so I'd be excited to see what happens for machine teaching, for example.
Very cool. So as I understand it, data modeling it's like a black box method where we have a surrogate model. And the model is a function of the algorithm, an input example, and some training subset, and it's predicting the output of the training and evaluation of the model. So the first thought is these models are really complex, and we're just building a linear surrogate function. Does it work, and how well does it work?
Yeah, I would say it works surprisingly well. It's obviously not perfect, but across a bunch of data sets we've tried, what you can look at to evaluate data models is actually just basically the correlation between what you say is going to happen according to your data model and reality, which you can access by just training the model yourself on that data set. And so there are two sort of interesting ways of evaluating these. One is that we fit the data models by sampling a bunch of random data sets, training a model on each one, and then fitting basically a linear regression from the 1-0 encoding of the data set we trained on to a model's output on a specific target. It doesn't have to be a linear regression, but in our paper we did a linear regression. And so the nice thing is this is just a linear regression problem. You can sample a bunch of new subsets. You can see what your data model predicts. You can measure reality. You can compute the correlation. And so as I was saying, there are two interesting ways of evaluating this. One is this like on distribution evaluation, where you sample data sets from the same distribution of data sets that you use to fit the parameters. And there, data models do like amazingly well, like way better than we ever would have thought. Like on CFAR10, for example, the correlation between data model predictions and reality is like 0.9 or something like that, which is strikingly linear, I think. When you go to non-random data sets, because I think that's sort of the more interesting question, is like, does this work once you leave this distribution of data sets that you sampled? The answer is yes, but slightly worse. So the correlation degrades a little bit, But trend-wise, we tried a bunch of different ways of like breaking the data model. So like, can you try selecting the worst examples? Can you try selecting the best examples? So like all of these very highly non-random data sets. And what we found is that across the board, these things worked pretty well. And I would say follow-up work that we've done shows that it works not just for CFAR10, but across a bunch of other different data sets, although how well it works for different data sets has varied a little bit.
Yeah, interesting. Because neural networks learn statistics of increasing complexity as you train them for longer and as the models get bigger and so on. And do you notice some, like for example, would a linear data model bias on simpler features, or does it seem to work on more complex models as well?
As far as we can tell, it seems to work on more complex models as well. We've tried scaling up the models pretty intensely. And actually, there's sort of this folklore intuition we have, which is completely unverified. So take this with a grain of salt. But if you sort of think about when, as deep neural networks sort of grow in width and in over-parameterization, this like linear approximation in their parameter space, tends to work better and better. They sort of look more linear in their parameter space, and there's an interesting connection between linearity in parameter space and linearity in data space. We sort of know that this linear approximation in data space works really well for very over-parameterized linear models. And so, again, folklore intuition is that as your deep neural network approaches a very over-parameterized linear model, this like linear approximation actually works even better.
Very cool. So you're building this like supervised regression model, and you're sampling subsets of the data to train it. What's the kind of the methodology there? Like, how do you sample the subsets?
Yeah, it's a great question that we thought a lot about. And I think in an ideal world, you could come up with like a really smart adaptive sampling algorithm for this problem, right? Because you sort of know where you need information and where you don't need information. You can think of each subset that you sample as giving you some extra information about the value of those data points or something like that. Unfortunately, I think because of sort of the way our compute is structured, that like we have tons of GPUs available at once, and so we like to saturate them all. We basically just did completely oblivious random sampling. So, we have like however many GPUs, and we just sample a bunch of random data sets of fixed size and train in parallel across all of the GPUs.
So on this surrogate model, I mean, what is a good output to track, if that makes sense? I mean, let's say we're doing classification or something like that. What should we track?
Absolutely. There's a little bit of, I would say, like manual science there, in the sense that we sort of had this intuition that, okay, if we're doing a linear regression, then probably we want something that ranges from -infinity to infinity. We thought about doing a logistic regression, but then we thought, that's kind of throwing away some amount of information, because 0 or 1 is a much noisier signal than like your exact loss or something like that. And so we ended up settling on what we called like this correct class margin, which is just the logit of the correct class minus the next highest logit. And I think there's still, like, I wouldn't say that's super, it's not clear that that's the optimal thing to track, but we generally have these sort of principles that, okay, it should be something that ranges, all the whole real number line. It should be something pretty dense with information, so not throwing away bits from, the actual logits as much as possible. And so using all of that stuff, we kind of settled on this correct class margin.
So what's the difference between, because obviously we're talking about this surrogate model that has this, more abstract notion of dataset statistics. I mean, how does that compare to just say, doing analysis on a specific model?
Yeah, it's a great question. I think the core thing to realize here is that when you do this like dataset level analysis, the thing you're actually studying is not a specific model, but it's actually a learning algorithm. So you're not studying like a specific ResNet. You're really studying like the process of training a model with a ResNet with SGD, which produces a whole class of models basically, and whatever features you extract or whatever analysis you do is really in aggregate over that whole class of models. And I think the distinction becomes kind of important when you're sort of asking. It makes it harder to apply this to questions where you care about like this one specific model.
So when we've got this data model, what kind of stuff can we do with it?
Yeah, so I think in our original paper, we had a couple of what I now think are like slightly more toy applications. So like it works for examples, a pretty good similarity metric between examples. We used it to find like train test leakage and things like that. We use it actually to do like a deep learning analog of, there's this really nice paper out of MIT a few years ago where they studied, it was a statistics paper, but they studied a bunch of like, published experiments like from the social sciences and stuff. And they found that by removing just a couple of data points from these surveys analyses, they could flip the conclusions. And so we basically were able to do the same thing in the context of deep learning by using data models. So figuring out like which exact training examples do you need to drop to flip a model's prediction on a given test example. So I'd say those were sort of all of the original applications of data models. I think the ones that I'm more excited about now, as I was mentioning earlier, the ones that I'm more excited about now are more of the flavor of you have some property that you want from your model. And that property can be written as a function of the data set that it's trained on and as a function of model predictions. And so, for example, like, dataset selection or even machine teaching. But if you think about dataset selection, you can sort of write like, okay, I want, max over dataset of model performance. And so, that's obviously a very expensive problem to solve manually because, inside this maximization, you have like the entire model training process. But if you can take that model training process and replace it with a data model prediction, then it becomes a much more tractable optimization problem.
One of the things you looked at in the paper was the strength of the embeddings of the data model, versus using, say, the penultimate layer, in the original model. How does that work?
Yeah, so I think one very nice thing that's a little bit specific to these linear data models is the fact that after you estimate them, what you have is sort of a vector whose length is the size of whatever pool of data you're sampling data sets from. And the nice thing about these vectors is that each index in the vector corresponds to a single training example, and the value of that index is exactly how important that training example was to a prediction. And so what that means is that you can actually estimate these vectors for, one learning algorithm, and you can estimate them for another learning algorithm, and the resulting representations that you get sort of mean the same thing by default. So you can, component-wise compare these representations. And we actually had some follow-up work led by a great student in our lab where we used this exact property to compare different learning algorithms, for example. But I think, this idea that you have, these two, what I call like two really nice unique properties. One is this, universal interpretability of the embeddings, and the second is the fact that, not only do the individual coordinates mean something, but the vector as a whole you can treat as a predictor of how the model is going to behave. These two things together, I think, allow you to basically, extract a lot of cool insights about, again, learning algorithms.
Yeah, so what did you find? So, I suppose you can compare classes of learning algorithms, but these are also, potentially class specific. So could you use them to kind of figure out confusion between classes and stuff like that?
Yeah, absolutely. So you can always, you can use this to analyze like a specific learning algorithm and try to understand sort of like what its failure modes are and things like that. When we compare it to sort of two different learning algorithms or two different classes of machine learning models, what we're doing is basically looking for systematic differences in these data model vectors and using those to try to understand like, okay, well, for what subpopulations does one model class or one learning algorithm work substantially differently from the other?
Cool. And what else are you excited about in this space?
Yeah, I think the big next steps, I'm obviously still working on this space. I think I'd highlight like three big next steps. One is just making this more efficient and more performant. Like the data model estimator in its original form requires you to train, tens of thousands of machine learning models on random data sets, which is not ideal. And we have some follow-up work called TRAK making this faster, but I think we really haven't hit the limit. There's still a lot of room for improvement. And right now, we're working on better, faster versions of this data modeling problem that I think are going to be really exciting. The second thing is finding applications specifically sort of in data-hungry regimes that we maybe don't normally think about, sort of like outside of vision or even outside of language modeling. But thinking, for example, about thinking about robotics, thinking about like scientific measurement type stuff, where really like pointing your telescope somewhere and taking a picture is like a very expensive thing, and you want to know exactly where you should do it. So I think like applying it to those outside domains that we don't usually think about is something else that's really exciting.
Yeah, and how might that work, for example? So, I mean, if you were to apply this to something like reinforcement learning, I mean, what would that look like?
Yeah, it's a really good question that I think needs a little thought. It's not clear directly how to apply it. I think like there are sort of midpoints between supervised learning and reinforcement learning where maybe it makes slightly more sense, like an offline RL, for example, looks much more like supervised learning. But in terms of applying it to online RL, it's kind of difficult because you need to figure out what it means to sample a subset of the space. One sort of broad class of ideas that I haven't explored at all, but I'm really excited about thinking about, is you can sort of imagine generalizing this framework to predict not just as a function of what exact data points you train on, but if you have some like parametric representation of how you're going to collect data, and you learn the map from that parametric representation to predictions, then it's possible maybe to apply this beyond just the supervised learning case. Because I think the knobs you have to tune in, RL, for example, are not quite just like include or not include data point, but there are knobs that you can still tune.
And this brings us on nicely to TRAK, which is your kind of evolution of this data modeling work. Can you introduce it?
Yeah, of course. So as I mentioned, training and fitting these data models is quite expensive. You need, in their original instantiation, you need tens of thousands of machine learning models trained on random data sets. And so together with Sam Park, Christian Georgiev, and Guillaume Leclerc, and our advisor, Alexander, at MIT, we basically were thinking about how we could make this more efficient. And the key is really to go back to this influence function work that you were talking about earlier, which, as we were talking about, works really well for these classical statistical models like linear regression or logistic regression. But the assumptions that they rely on don't really hold in like the deep learning setting. And so our main idea was actually this two-step process where we're like, okay, first what we're going to do is we're going to approximate whatever neural network or whatever class of neural networks we're interested in studying. We're going to approximate them as over-parameterized logistic regressions. And this is a well-known approximation called like the empirical neural tangent kernel. But the idea is you basically look at where your network ended up, you look at those final parameters, and then you do a Taylor expansion in parameter space to basically what's called linearize your neural network. So you really treat it as a linear function in parameter space. And so what this allows you to do is now that we're back in linear function land, we can then go back and try to apply the influence function. And so, this plus a couple of other very important tricks and analyses allow us to basically build an estimator that works, roughly about as well, like in relevant regimes, about as well as a regression-based data model at, 100x less computation or even 1,000x less computation.
So you said that this model that you've built now, TRAK, can work for parameterized differentiable models. And I think you said of a size roughly commensurate to about 300 million parameters. Is that roughly right?
Yeah, that's right. So in our paper, at least in our paper, we tried up to 300 million parameter models and got some pretty promising results. I think we would like to do a lot more work on trying to understand sort of like where the limits are of this. The TRAK estimator for data models is definitely more efficient in the sense of like if you train with 1,000 less models, it'll work about as well. But it's not going to be sort of like its limits are not going to be as good as you could get with this regression-based estimator. And so I think trying to understand the limits and also trying to understand when or where it doesn't work or does work, I think is a great direction for future work.
Yeah, I mean, because you were talking about this trade-off between speed and efficiency. I mean, can you tell us about that?
Yeah, so I think part of the nice thing that we did in the TRAK paper is crystallize some of our thoughts from the original data models paper about like how we should actually go about evaluating these like broad class of data attribution methods. And so there are I think one broad problem in general with data attribution is that if I come up to you with some method for, some data model and you come up to me with some other method for assigning value to data points, there's not really a great way of deciding whose is better. And so I think one thing that we tried to put forward in the TRAK paper, and this is almost taken directly from the original data models paper, is that the way we should evaluate these things is by using this correlation that I was talking about earlier between predicted model outputs and true model outputs. And so once you do this sort of quantitative evaluation of data attribution methods, it sort of allows you to see this existing trade-off that was present in the literature between fast methods that were not super predictive of model predictions or of model behavior, and extremely slow method like the regression-based estimator that I was talking about that were very predictive of model behavior. And so you can sort of now view this goal of data attribution as like trying to trace out better and better Pareto frontiers of this trade-off between efficacy and speed.
Yes, and the first one you did in your paper was this LDS score, this linear data modeling score. How does that work?
Yeah, so that's exactly this correlation that I was talking about.
Yeah.
So what that looks like is the thing you're evaluating is some function that maps from a test data point to a vector of scores, one for each training data point. So this is like broadly what was recognized at the time as like a data attribution method. And there are a bunch of these. Like you were saying, like there's the Shapley value, there's the influence function, there's a whole bunch of these. And the neat thing about all of these is that they all have an interpretation as a linear data model. So they all the sort of the thing that inspired them, so the right way to interpret them is as coefficients of a model that tries to predict these data counterfactuals. And so we were like, okay, if what these things are doing are trying to predict data counterfactuals, then the way we should evaluate them is basically we should try to tell how good they are at evaluating data counterfactuals. So the LDS is exactly generating a bunch of data counterfactuals, seeing what these different methods predict will happen under those data counterfactuals, and then looking at the correlation between predictions and reality.
So can you explain the derivation?
Yeah, of course. So like I was saying, that the key idea behind TRAK is really this approximation of your neural network as a linear model in parameter space. And so if you sort of take a step back and you think about what if we were just doing logistic regression? Like what if there were no neural network or anything? It turns out that in this case, like we were saying earlier, the influence function is a really good data model. It's a very good approximation for getting data counterfactuals. The problem is that we're not doing logistic regression. We have this like crazy big neural network or whatever. So let's start with thinking about a two-class neural network. So this is still like a binary classification problem, but now we have a neural network instead of logistic regression. What we can do is we can train that neural network, or like we can apply our learning algorithm once and we get a neural network. Once we do that, that neural network has a corresponding parameter vector theta, which are just the weights of all the neural network. What we're going to do then is treat the output of that neural network as a linear function in theta by doing a Taylor approximation around those final parameters. So what that looks like is if your normal neural network was like f of theta, you're going to make a new neural network that looks like f hat of theta, which is now a linear function in theta plus which is now a linear function in theta times your gradient evaluated at theta star. And so this is a very classical trick, especially in deep learning theory. It's called the empirical neural tangent kernel. And the nice thing is once you've sort of done this linearization, what you have, this f hat, is now a linear function in your parameter vector theta. And when you have a linear function in your parameter vector theta, the influence function comes back on the table. Now there are a couple of tricks that we need to do here because first of all, like I was saying earlier, we're trying to study the learning algorithm, not necessarily a specific model. But the thing I just described is only a single model, right? And so what we actually need to do is apply this whole process of like train a model, get the final parameters, do a Taylor approximation over and over and over, and compute the influence function over and over and over again, and then ensemble the results. The second thing we need to do is these gradient vectors that we're going to use to compute the influence functions are huge. They're the number of parameters in the neural network because the linear approximation we've made is linear in the parameter space of the neural network. And so if we want to get around that, what we originally proposed was randomly projecting those those gradient vectors down to some manageable dimension before applying the influence function. And so those two extra tricks, ensembling over several trained models and randomly projecting to a smaller dimension, turn TRAK into an actual tractable estimator for data models rather than like a theoretical conception. And what's interesting is that after releasing TRAK and sort of doing a bunch of experiments, we've actually found that like even though we originally did these random projections as like a time/space saving, cost-cutting measure, basically, it turns out that the random projections themselves are doing something very non-trivial and kind of important for TRAK. And so understanding that exactly would be very nice.
Can you expand on that?
Yeah, so generally when you're doing random projections of different vectors, you think of it as sort of like a lossy compression metric, basically, right? Like what we wanted is this influence function computed on gradient vectors. We can't do that because the gradient vectors are too big. So let's instead, randomly project these gradient vectors down to a manageable dimension, and then let's do the influence function on those. And so what you'd expect if that was your mental model, what you would expect is for things to generally get worse as the projection dimension goes down, because you're progressively losing more and more information from these random projections. What we find though is that there's actually sort of like this peaking behavior, where for a while making the random projection smaller actually gets better and better, and then it starts getting worse. And so what that indicates is that there's actually some, non-compression effect of the random projections that we're doing. They're adding something. And so there's a lot of really interesting work out of a couple of groups in like the statistics community that suggests that actually like doing the influence function on randomly projected vectors is equivalent to doing some sort of like regularized influence function on the original vectors. And so there's some regularization element or something like that happening that we didn't originally account for when we were writing the TRAK paper.
Very cool, very cool. And you also did some experiments with language models.
Yeah, so that's probably my favorite application from the TRAK paper is that we took this data set, which is this brilliantly designed data set out of MIT. I think Ekin Akurek is the lead author on that, out of Jacob Andreas' group. But they designed this really cool data set called ftrace. And the idea behind ftrace is that they construct this artificial data set where you have a test set that contains a bunch of facts and a train set of Wikipedia abstracts. And they have annotations for which abstracts entail which facts. So for example, in your training set, if you have, like France is a country whose capital is Paris, blah, 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 blah. And then in your test set, it says like, what's the capital of France? Paris. Then like that would be labeled with a logical entailment. And so the really nice thing about this data set is it sort of gives you this technique for evaluating different data attribution methods by saying, okay, if I take this test example where the test example says what's the capital of France, Paris, and I look at sort of like what the most important examples are for that test example, it should highlight the things that entail that fact.
And what does that look like? I mean, how interpretable is it in practice?
Yeah, so in practice, what they found in their paper, which came out a while before TRAK, is that like an information retrieval system beat every single data attribution baseline they tried. In particular, like the data attribution did not work well. Like all of the data attribution methods just performed really poorly according to their they like measured basically the overlap between what your data attribution method claims the most important examples are compared to which, looking at the overlap between that set and the set of actually logically entailing training examples. And they found that everything performs really poorly. And so, we saw this before writing the TRAK paper and we're like, this is a perfect test bed for trying out TRAK. And so we tried it out and we found that there was a higher overlap than any other data attribution method, but it was still getting beat by this information retrieval baseline. And so we were like, okay, can we do something like what's going on here? Because we shook our faith a little bit in our method. We were like, maybe we're not actually finding anything meaningful. And so we took their exact data set and we designed this slightly alternate evaluation metric where we say, okay, instead of like just measuring the overlap with the ground truth facts, why don't we try removing the examples that are flagged by our method and then retraining the model and seeing how many of the test facts that model gets wrong. So if you actually identify the right things, then when you delete them, your model should get the corresponding test examples wrong. And so you can try this, for example, for the top 100 TRAK identified training examples, and then you can try it again for the top 100 information retrieval training examples. And then as a baseline, you can try dropping out all of the ground truth, entailing facts in the training set. And for each of those counterfactuals, you can study sort of what the model's behavior on a test example looks like.
Yeah, that would be really useful for concept scrubbing.
Yeah. So it's a very similar, basically the evaluation mirrors a lot like, can we scrub certain test examples? And so, once we've done this counterfactual evaluation, what we found is actually that the TRAK identified training examples had a larger counterfactual effect on the outputs than any of the other data attribution methods, than the information retrieval method, and even than the ground truth facts. And so this is really confusing. There are a bunch of sort of explanations of this in our paper for why we think there are a lot of sort of syntactic relationships that are not entailment relationships in the data set. I won't go into detail about that here. But the interesting thing is that, we found that TRAK was a really effective tool for sort of finding the most important training examples for a given test prediction.
Yeah, interesting. I'm thinking of that Anthropic Golden Gate Bridge example, and they had this unsupervised method of finding salient features, and then they actually showed you the attribution in the source data, and they were saying that this is evidence that the models were learning high level abstract features, but they seemed quite low level to me. I just wondered what's the level of abstraction you're seeing with the data attribution?
Yeah, that's a fantastic question, and actually one of the inspirations for developing the whole data model framework is that we wanted to understand sort of this there's the spectrum between very exemplar based prediction of I see this dog because I say this is a dog because I've seen a similar dog before, and the sort of abstract high level feature learning. And we wanted to actually go about testing that hypothesis. We wanted to see at the test set level, how many features are learned locally or on an exemplar basis versus how many are sort of these abstract features. And what we found is that there is a good core of what you might call abstract features. It's hard to actually pin them down as abstract features, but at the very least, there's a good core of images or of examples that are learned very robustly. And so if you sort of look at what the data attributions for these examples look like, they're very dense in data space. They're sort of abstracting from a lot of different training examples. But there is sort of a very significant tail of examples that are learned, that seem to be learned at least in a very exemplar way. So there are a bunch of examples for which you can remove 10, 20 out of 50,000 training samples and flip a model's prediction on those test examples, sorry.
Yeah, I mean, this might be a nice segue, but I think you would call that long tail of exemplar features non-robust features. But maybe we should just back up a little bit. I mean, define abstract feature. I mean, what does that mean to you?
Yeah, so I don't have a great conception of what that is. I think it very much also depends on the context in which you're talking. I think when people think about, like you were saying, there's this notion of robust versus non-robust features in the causal sense. There's robust versus non-robust features in the adversarial sense. Now the thing I was just talking about is a notion of robust versus non-robust features in the training data sense. And so I think for each of those senses, you can sort of define what it means for a feature to be robust, but I don't think we really have a great conception of what exactly a feature is. And as far as I can tell, it's something we struggled with a lot in the adversarial examples work. Every definition of feature ends up falling short in some devastating way. So it's I think a continuous challenge in machine learning to really write down what we mean when we say feature.
Yes. What is the relationship between, abstraction and reasoning? I mean, do you think neural networks reason?
That is a fantastic question. Luckily, not one that I've had to think about much for my own research. I think that the reason why this is such a confusing question is that I don't think, as far as I know at least, I haven't really seen a convincing concrete definition of either abstraction or reasoning. And so it makes it kind of difficult to equate one or the other because I think people can, I can come up with a paper that says here's abstraction, here's reasoning. They're not the same. Or neural networks do one and not the other. And then, someone else can come up with a paper that's like, here's reasoning and here's abstraction, and neural networks do one and the other, or one and not the other. And I think it just makes it very hard to pin down, like, what is it exactly we're looking for. But I think in this, like, pursuit of, like, reasoning systems, actually writing down what reasoning means is, like, a very important and noble goal.
Let's just, put my cards on the table for a second. Let's say abstraction is some form of compression, and the statistical interpretation, we can debate whether it's in distribution or out of distribution. And reasoning is the ability to create a new model, create new knowledge. So I think when people talk about reasoning, that they're saying that the model is somehow compressing representations and then building new models, maybe some kind of structural learning, so that it can apply that knowledge in a new situation.
Okay, so I think by your definition of abstraction, that's like something we believe current neural networks do, at least to some degree, because they fit giant training data sets that are probably more gigabytes than their parameters are or something. And so the question you're saying is whether that is enough for reasoning, or is the question whether current neural networks reason?
Some people say the kind of the deflationary take is that neural networks just, you scale them up and they learn more of the long tail, and they're just basically memorizing loads and loads of data. And the other take is that, through the machinations of prompt engineering and the auto-regression, there's some kind of like meta learning going on, and it's performing an effective computation as if it's doing reasoning.
Interesting. Okay, I think I'm getting a better sense of the question, which is a really interesting one, and one that I think the sort of tools we're building will hopefully be helpful for answering, because I think fundamentally, like, if you're trying to disentangle those two things, what you need to understand is not just what the behavior of the neural network is, but you also need to sort of understand, like, what's driving that behavior. There's this idea that, like, when you're training on, like, I forget who said it, but someone was like, you have no idea how big the internet is. Like, if you think about a neural network trained on the entire internet, like, you have no idea how much data that is. And so, the interesting thing I think about that quote is that it can be interpreted in two totally different ways. One is you could be like, you have no idea how much data that is. Like, clearly this, like, emergence of reasoning could happen because of how much data that is. The other is that, like, you have no idea how much data that is. Anything you see is just going to be in the training data. So there's no, reasoning or emergence of reasoning necessary. It's all just going to be there. And I think disentangling between those two things requires looking beyond performance into things like, trying to understand where in the training data predictions are coming from, trying to understand, like, what exactly are the steps of a problem that were present in the training data versus what's new. And for what's new, like, where is that new behavior actually coming from? And so one particularly interesting direction, I think, is trying to understand from a data perspective where exactly these, like, surprising, amazing advancements of large language models are coming from, because they're clearly not I think it's slightly reductionist now to say that they're, like, copy pasting from the training data, but, like, that doesn't mean that, like, they're reasoning, or it doesn't mean that anything crazy is happening. It could just be that, like, they've learned a good enough abstraction to copy paste from the training data in, like, a much more abstract way. And then you get into this philosophical discussion of, like, is that what humans are doing? And I don't want to think about that.
I know, as you say, there's a prodigious amount of data, unimaginably large, and the networks genuinely are doing, extrapolation. So we're addressing this ridiculously large set of, space of information, if you like. But the problem is, it's very difficult to distinguish kind of simulating or memorizing reasoning versus actually doing it, which is why work like yours is so important.
Yeah, I think I totally agree, and that's a big driving force, I think, behind our work. I'm very curious to see sort of, like, what happens when you apply the methods we're developing to these large, language models, and, the ones that we claim are doing reasoning and things like that. I think the only thing stopping us right now is just not having quite fast enough methods to actually scale. I think there's a really nice paper out of Anthropic that exactly tried to do this for Claude, I believe, sort of understand where different behaviors are coming from the training data. But even then, I mean, these methods are so expensive that I don't think they were able to do, for example, like, actual data counterfactuals, or, like I think most of the analysis was done on a smaller version of Claude that they then, had to extrapolate to a larger version. And so there are all of these things that are, I think, fundamentally right now just like engineering, clever methods. But I think as we sort of scale up and get these methods to compete with the size and scale of models and data sets, I think there will be a lot of cool stuff we can learn.
How do you feel about this? So you're an MIT researcher, and obviously I'm sure MIT has like massive amounts of compute resources and so on. But obviously you could go and work for Anthropic, and they've got even more. But there's always this notion that you're a little bit restricted. So we're building smaller models of analysis. I mean, in a perfect world, would you just like to have OpenAI's compute cluster and you would play with that?
Yeah, I think they're just fundamentally different questions that you ask at each scale. Like I think by choosing to be in academia, like perhaps I have more freedom to do things at small scale, but I'm not going to be able to run the experiments that OpenAI are running, and to some extent that is a barrier between academia and industry. But I think that the way that academia has to deal with that is by sort of prioritizing different questions. Almost in the same way that we have like Boeing and then we have like aerospace engineering professors that aren't building commercial airliners. They're just fundamentally different questions that emerge at each scale. And so I think what I hope academia can do is like really try to understand, like, are there things that hold across scales that we can then verify at very large scale? But I think a lot of the problems that are currently in machine learning of like, the things you see in ChatGPT, like bias, hallucination, incorrect facts, all of these things are problems we can study at small scale and try to make predictions about.
Yeah, I think it's interesting because having all of that compute almost makes you intellectually lazy. So the easy thing to do is just to run bigger and bigger experiments. And that's why I love a lot of the work out of MIT. I don't know if you know like Kevin Ellis, under Josh Tannenbaum, and he's doing this dream coder thing, for like program synthesis. And even though at the moment the results are not state of the art, I just love this idea of having a principled approach. And I think that it will pay off in the long run. And so I'm really happy that there are folks like you actually, doing theory and going to first principles.
Yeah, absolutely. I mean, I totally agree. And I think a lot of that work is really, really cool. And I think in general, I think this is definitely a thing in design. They say like constraints breed good design.
Yeah.
Because there's always the thing you could do of just like, what happens if I scale this method up 1,000x? And I'm sure it does better than it does now. And I think there are really interesting questions. I truly think there are really interesting questions that can only be studied at sort of the OpenAI scale. But I don't think we're at a lack of interesting questions that can be studied at our scale. I think there are tons of them.
Amazing. Well, going back to the features thing. So we're talking about the kinds of representations these models learn, and how robust they are. Now, you wrote a landmark paper a few years ago called "Adversarial Examples Are Not Bugs; They Are Features." This was really good. I learned about this from Hardy Salman. I had him on the show. Can you explain what this paper was about?
Absolutely. Okay, so taking a step back, the context here is we're looking at adversarial examples in the vision context, which is this phenomenon where you can add a very small perturbation to a natural image, and by adding that small perturbation, a machine learning model that normally does very, very well will consistently misbehave whenever it sees these perturbed images. And so we were trying to figure out why, and I would say that the paper is sort of centered around one experiment and one result that we found particularly surprising. So just to set the stage a little bit, I think at the time when we were writing this paper, the sort of conceptual model that people had of adversarial examples is that they were somehow what we refer to as bugs. But you can think of these in a variety of ways. They're essentially like when you perturb these make these adversarial examples, you're really sort of like there are a bunch of words for it, like leaving the image manifold. You're sort of adding something. You're adding something useless. There's this intuition that when you train a neural network, it learns a bunch of useful features, and then it also is sensitive to a bunch of useless features. And that could be because of overfitting, could be because of finite sample error. It doesn't matter what. And then the intuition went, okay, well, now that you've learned a bunch of useful features and a bunch of useless features, an adversary can come in at test time. They can change all of these useless features. They won't have changed anything about the input, which is why it looks the same to us. But the machine learning model that depended on these useless features is now going to be completely misled. Okay, so that's the conceptual model sort of going into this work. And what we really wanted to do was test this out. And so we designed this really simple experiment. We took a data set, just a standard image classification data set, and we took the training set, and we took a fixed model, and we made an adversarial example out of every single sample in the training set. So what that means is that, like, let's say, for simplicity, let's say you just have like a dogs versus cats training set. Every cat you adversarially perturb to become a dog. Every dog you adversarially perturb to become a cat. And so the result is like this data set of, like cats that have been slightly perturbed to be classified as dogs and dogs that have been slightly perturbed to be classified as cats. Now, once you've done that, what we're going to do is we're going to relabel the data according to the adversarial class. So the resulting data set looks completely misclassified to a human. You just have a bunch of cats labeled as dogs and dogs labeled as cats. Of course, these are all like slightly perturbed images. We then, throw away the original model and we throw away the original data set, and we just train a new model on this data set of, mislabeled dogs and mislabeled cats. And the question is sort of like, what's going to happen with this new model if we test it on the original data distribution? So just clean pictures of cats labeled as cats and dogs labeled as dogs. And if you think back to this, useful versus useless features dichotomy, you should basically only expect two things. Either the classifier will get 0%, because, you've trained it on a bunch of cats labeled as dogs and dogs labeled as cats, and you're testing it on correctly classified images. Or, maybe you're slightly more skeptical and you're like, well, actually, I think it could get 50%, right? Because it's possible that by making these adversarial examples in the training set, you're actually sort of like introducing some variation along the useless features, and then the model might just like cling to that useless variation and then get 50% on the clean data. The interesting thing, though, is that when you train a classifier on this entirely mislabeled data set, that classifier gets 90% accuracy on clean pictures of dogs and cats. And so what that means is that this like useful versus useless features dichotomy is not enough to explain what happened here. There has to be something else at play. And so, by doing that, by doing this experiment, we basically, gave support for this model of non-robust features, whereby not only are there useless features and useful features, but there are actually within the class of useful features, there are features that are genuinely useful for the classification task at hand, but just happen to be not robust to small perturbations. And so like a very toy example of what that would look like is, imagine if there were like a small pixel in the top right of every single example that told you exactly what the class was. Then like you wouldn't have to learn anything about the image. You could just get 100% accuracy by looking at this pixel. But if you did that, an adversary could come in and by changing just that one pixel, completely flip your classification. And so what we're showing is that, obviously this one pixel scenario isn't real, but there are features like this in sort of standard image data sets.
It's a fascinating thing about neural networks that, as you say, you can actually randomly assign labels, not even in a consistent way, and the neural network will still get 100% accuracy on the trained set. And I guess that's because if you think about it, the neural networks have enough flexibility to kind of place decision boundaries around each of the individual training examples, so they could basically memorize your training set a bit like a zip file or something like that. So there's the spectrum, isn't there, that you can on the one side you can memorize examples, and then going up a little bit on the spectrum you can memorize features. So like these weird blue dots that you're talking about. And then somewhere up on the spectrum, you end up with, robust out-of-domain generalization features that actually represent the thing that you want. So I guess like the question is, how do you know the difference between, it just memorizing examples versus non-robust features?
That's a great question. I think it gets back to this, this idea of sort of like disambiguating different notions of robustness. And so, ideally, we want our models to be robust in every sense of the word robustness. Like we'd like, if they were truly learning sort of like human level features, then we'd want them to be adversarially robust, because humans are adversarially robust. So we'd like that. B, we'd like them to be like sort of data space robust. And that's sort of what we were talking about earlier, that like, your prediction should not hinge on like one or two examples being removed from your training set, because that feels like kind of this exemplar based, not really abstract, like this memorization behavior that we were just talking about. And then 3, which is something that, I haven't explored, but also I know, is being explored right now. You also want them to learn features that are causally robust, in the sense that like you want it to learn to avoid like, spurious features and, generalize out of domain and things like that. And I'm sure there are other notions of robustness as well. And the interesting thing is each of these robustness problems is on its own like a huge challenge. And what we actually want is like the union of all of these different notions of robustness. So I think we're a bit a ways from that, but a really interesting problem.
Yeah, so how did you go about, mitigating the robustness problem in the paper?
Yeah, so in the paper we studied like a very common algorithm for trying to deal with adversarial examples, which is this adversarial training or robust optimization algorithm. And the idea behind that algorithm is that as you're training your model, at each stage, rather than training on clean inputs, you train on adversarial examples for the given model. And so what that does is basically turn your original sort of like loss minimization problem that you're solving when you train a neural network, you turn it into this sort of robust optimization min-max style problem where you're now finding parameters that minimize the loss on the worst case image rather than the loss on the average image. And what, like, under this sort of robust, non-robust features view, I think you can sort of view this robust optimization or adversarial training algorithm as basically like beating the non-robust features out of the neural network. Because if at any point the neural network relies on a non-robust feature, that non-robust feature can be exploited by the adversary and, forced to point the other way. And the network will sort of learn, okay, I can't rely on that feature. I can't rely on this feature. I have to rely on these more robust features.
Yeah, and I'm thinking about the different approaches. I mean, hypothetically, you could pre-process the data before it even goes into the model. You could change the optimization algorithm of the model itself, or given a trained model, you could kind of like, robustify it. So you're talking about the middle option where you're actually changing the optimization algorithm.
Yes, absolutely. I think for the other two options are really interesting. I would say that there's been significantly less progress along those other two options. The first option, I think, is really compelling, and we actually showed that, we showed in this sort of adversarial examples are not bugs, they're features paper. We showed a way of pre-processing data to get you a very small amount of robustness using an existing robust network. But I think the core challenges there is that we have a very poor handle on like features in natural images. Like we don't really have a way of like, if you think about what's the space of features for an image, it's basically infinite. And we don't really have a great way of like removing a non-robust feature or adding a non-robust feature or anything like that. The fine-tuning or like robustifying networks post hoc is really interesting and has been a big source of study. I think that there has been some work trying to do this via like, randomized smoothing at test time, for example, or by like fine tuning the network using a robust objective or something like that. But I would say we've had less progress on that than sort of like algorithm focused approaches.
Yeah, I mean, I'm interested in the different types of features as you were just alluding to. So Randall Bellistriero yesterday, he had this paper which was talking about the difference between reconstructive methods like, let's say a masked autoencoder versus, a self-supervised contrastive image representation learning model. And he said the problem with the autoencoders is they bias towards low frequency data, which is like, it looks like quite blurry kind of data. And you can mitigate that by just adding some pink noise or something to the image to try and, convince the model not to learn, so much of the mass of the low frequency data. And there has been discussion about, for example, we tend to look at, like shapes and objects, and image classifiers tend to kind of look at, textures and stuff like that. So I don't know, how do you kind of think about different types of features that these models learn?
Yeah, it's a fascinating question. I think there are a lot of people studying this sort of like inductive or implicit bias as well, which deals with like a very similar thing. And I think all of these are sort of getting at this core problem that the space of features that neural networks can learn is, unfathomably large because of, how over parameterized they are and the fact that they can, for example, memorize the entire training set with random labels. And so they have almost infinite features to choose from. And so there's this interesting question of like, okay, if we just, leave things alone and we just run SGD with this architecture, what features will this network actually converge to? And I think that's almost like a more relevant question than like what features can they represent? Because the answer to the latter question is almost always like any feature. And so you can view like, I think, I know the work you were talking about like the masked autoencoders. You can view this as like sort of what knobs do we have to change neural networks' inductive biases? And similarly, like the paper by Rob Garros, the texture versus shape bias one, they similarly sort of like we're trying to figure out sort of like what knobs do we have to play with to change this texture versus shape bias, whether that's the addition of training data that has different styles with the same class, and I think a really natural perspective to view like adversarial training from and robust optimization is exactly saying like, okay, the inductive bias or the implicit bias of our neural networks is leading us towards features that are great, just happen to be not adversarially robust. And so you can view adversarial training as basically trying to change those inductive biases so that they lead us towards features that are robust.
So when you do this, kind of robustness training, I guess what you're trying to do is selectively tell the model, don't learn these features, but do learn those features. And, and there's a variety of different ways of doing this, as we just discussed. But in a sense, you're kind of blindfolding the model. So the model now cannot learn all of the things it would otherwise have learned. So there must be like some kind of trade-off with the accuracy.
Yeah, absolutely. And that's something that was observed by a variety of papers before ours. Whether that's some like information theoretic loss of accuracy because you've, like you've said, blindfolded the model from a bunch of features is unclear because like on the one hand, we know humans can adversarially robustly classify images. So it's probably possible to get that level of accuracy. I think what really happens is some combination of, you're blindfolding the model from learning these features that it would normally learn, and you're basically asking it to instead learn a bunch of features that are much harder to learn robustly. And so there's this paper that I saw in arXiv just a couple of days ago that I think is at ICML, where they basically tried to build scaling laws for adversarially robust training. And they basically forecasted that if we had like 10 to the 30 flops, we could train, adversarially robust networks that are have state-of-the-art accuracy and like match human accuracy in terms of their adversarial robustness. But you need, tons of data and tons of compute.
Yeah, that's so interesting you say that because, again, when I spoke with Randall Balestriero, he's got this paper out, which is called something to do with spline theory gives rise to adversarial grokking. That's not the name of the title, but something like that. And he's got this idea that in the spline theory of neural networks, MLP networks, they partition the ambient space up into these piecewise constant locally affine regions in an input-sensitive way. And early on in training, when you visualize the ambient space and how it's being partitioned by the ReLU functions, it's just a complete mess. And when you train them for a ridiculous amount of time, so, much, much longer than any normal network would, you get this local decomplexification. So what happens is all of these boundaries they kind of compress into this kind of, it looks like a Voronoi diagram, like a kind of contour map, and you get more and more space outside the input examples. And maybe it's related to this double descent phenomenon, but something interesting happens if you continue to train neural networks for a long time. They robustify. Does that in any way go against the argument that maybe they are bugs?
Go against the argument that they are bugs, or go against the argument that
well,
they are?
I suppose like you could argue that they're not bugs, they're features. So all of these features are actually just shortcuts they're not statistically salient, they're just a form of overfitting. But there's also this like robustification, in the extreme of training regime. So maybe it's possible that it could both be true, that, there are features which are bugs, but also at a certain scale, we can just allow the statistical process to use them or not use them.
Yeah, absolutely. I think that the sort of core of the like features versus bugs question is really whether or not there exists information within sort of adversarial examples that's sufficient for good generalization within the rest of the data. It's sort of this question about like, are adversarial examples happening along some different axis than just like normal misclassified examples? And I think that like something that's, if I'm thinking of the right work, something that's both supported by that work and by our work is that there isn't really that significant a distinction between an adversarial example and any other misclassified input. Like when someone looks at a misclassified input, they're not like, oh, this is so mysterious. They're just like, okay, I learned the wrong features. Features happen to point the other way on this image. Tough luck, we'll get them next time. And so I think if you sort of think about adversarial examples from that perspective, what we're showing is exactly that on these adversarial examples, it just so happens that the features that your model learned are sort of pointing the wrong way. And I think it's really nice that this paper basically used adversarial examples and adversarial robustness as a way of studying just like the features used by a neural network. Something that I really appreciate.
Very cool. Can you tell us about your black box attacks paper?
Yeah, so that was one of the papers I mentioned that I did during my undergrad. When I first got hooked on this theory of this concept of adversarial examples, at the time, the space of attacks on adversarial examples was pretty much less mature than it is right now. There were, fast gradient sign method based attacks, which was just like take a single signed gradient step. There were, a couple of gradient based attacks, and this field of like gradient free or black box attacks was just emerging. And the idea here is that if you're an adversary and you're trying to attack like a production machine learning system, there's no way that production machine learning system is going to be like, here are our model weights, take some gradients, go ahead. What you usually have is like an API, some kind of thing where like you can query it with an image and then it'll reply with, here are the labels. And generally that threat model where you have only query access to a machine learning system was not sufficient to do adversarial attacks well. So there were sort of two lines of work emerging as we started that black box adversarial attacks work. One was on using adversarial transferability. So the idea is that if you wanted to attack a production model, what you should do is sort of like train your own model locally, attack that model, and then deploy the attack or like deploy the attacked image and see what happens. And so that was interesting, but sort of separate from what we were interested in. We wanted to see if we could really attack the system directly. And so there was one really nice workout at the time called, I think, ZOO, zeroth order attack, something with ZOO. It was like a zeroth order optimization based attack. And what they basically did is they would estimate the gradient by component wise, by doing like a zeroth order gradient estimator, which is basically like you start with your image. For each pixel, you like add epsilon, you subtract epsilon, you take the difference, you divide by 2 epsilon, and that's the partial derivative with respect to that pixel. You do that for every pixel, you have a gradient, and then you can use those gradients to attack a production system with only query access. And so our first black box adversarial attack paper was basically speeding that up or making that more query efficient, so you didn't have to spend tens of thousands of dollars in API credits, and also introducing this threat model where often it's not like you upload your image and then someone replies with a bunch of logits.
Yeah.
Instead, you usually just get sort of one prediction. Like I get to upload an image and then the thing tells me like this is a cat or like this is a dog, and that's all I have. And so we basically adapted these techniques to be used in the setting where you only have hard labels.
I actually remember, was that 2018?
That was 2018. Yeah.
I was running these paper review calls at Microsoft, and that was one of the papers we did. I actually remember now. Yeah, you're right, because you don't get the logit, so you have to do it in the kind of sparse domain where you don't have all of the labels.
Yeah.
Wow, that's really cool, man. Yeah. Amazing. I actually had read that paper, and you did another paper as well, which was faster black box attacks. So this was like an optimization, presumably, of that.
Yeah. So in the sort of first paper we did, which was during my undergrad, we're just focused on these two settings, like what we call the query limited setting, where you don't want to spend a bunch of money on APIs, and what we called like the hard label setting, where you have this sort of sparser information. But we weren't super focused on like optimizing the actual estimator very much. We just used like an off-the-shelf this like natural evolution strategies or spherical gradient estimator. It has a bunch of names, but we just used like a very standard sort of first zeroth order optimization algorithm. In this follow-up paper that I did during my PhD, which was joint with Logan Engstrom and our advisor, we basically looked at the algorithm itself for doing these black box attacks, and we subbed in this class of algorithms from zeroth order optimization called bandit algorithms, and we basically showed that by plugging in this class of techniques with like a super rich history and optimization, and plugging that in for what we were doing in the query limited setting, we could significantly accelerate black box attacks.
You've done loads and loads of work in the data collection part of that, predictive pipeline that we were talking about. Can you tell us about that?
Yeah, so I think if you sort of step back and view what we've been talking about so far, I think like the data models, data attribution stuff is really focused on understanding this like data set and learning algorithm stages of the pipeline. A lot of my work on adversarial examples is about understanding this final stage of the pipeline, and I have some other work on other aspects of the final stage of the pipeline. But really the missing piece is like, what if your data collection process itself is biased? And so I've done a lot of work both with Alexander on the more empirical side, but also with my other advisor, Kostas Daskalakis, on the more theoretical side of what happens when you're doing statistical inference or you're doing machine learning, and the way that you collect data is biased in some way. Can we find the ways in which that data is biased? And can we correct for it? So I can maybe give you like one highlight from each side, on the empirical side and the theoretical side. On the empirical side, probably my favorite one is this work that was led by two students who are now graduated, Dimitris and Shivani, Dimitris Tsipras and Shivani Santakar. And it was this really, really cool work that I was happy to be a part of that was about studying the ImageNet dataset, which like we think of as this sort of static, like representative, or we used to think of, at least at the time of this paper, as like this representative benchmark of image classification. And so we went in there and tried to uncover sort of like how the ImageNet dataset was collected, what possible biases could emerge. And in general, we found so like the way ImageNet was collected, just as a note, the way it was actually collected is that we scraped Flickr, or like the original authors scraped Flickr with a bunch of tags. So like for a given search term, they turned that search term, or they turned that class into a bunch of search terms. They searched Flickr for the search terms, and then they uploaded those images to Mechanical Turk and asked people like, does this image contain this class? Yes or no? And so as a result, there are a bunch of really interesting biases that kind of creep in unexpectedly from doing this. So for example, for confusing classes, like if there are two breeds of dogs that look very similar, because you're not actually asking people, is this breed A or breed B, you're just asking them, is this an example of breed A? Oftentimes people will just say yes. And so there are a lot of, for example, misclassified inputs in the ImageNet dataset. But I think what's even more interesting is these ambiguous classes that we found. So for example, like, I'm going to cite this wrong, but I think tie and suit and tie are two different ImageNet classes. And these each have their own images, but most of the images of suit and tie have a tie, and most of the images in tie are like someone wearing a tie with a suit. And so like if you show these to humans have a very hard time distinguishing between these two classes. But the interesting thing is that models trained on ImageNet are like much better than random at telling between these two classes. And so what that means is that not only was there this sort of bias that crept in at the data collection stage, but actually models have started picking up on this bias, and they're actually really good at doing it.
Where did those labels come from? If I understand correctly, there was something called WordNet, which was like a lexical database. And
Yes.
didn't they just like steal some categories from that?
Yeah, absolutely. So there's this lexical database called WordNet, and they basically went down the WordNet hierarchy. They sampled 1,000 sort of leaf nodes of this hierarchy, and then for each of those leaf nodes, they generated some search terms. They searched for those terms on Flickr. They took all the images they could find. For each of those images, they uploaded them to Mechanical Turk with this yes/no sort of like selection frequency type question, and they kept the images for which I think some number of annotators agreed contained the class. So they showed each image to multiple annotators, and then they kept all the images for which enough annotators agreed that, yeah, this is a good image of this class. So yeah, we had, that was just one of the findings, but we did this basically study into what kinds of biases can creep up as a function of how you collect data, not just like the data itself. And then on the theoretical side, probably my favorite work so far has been this work on understanding what's called self-selection bias. So this is, again, very far from the deep learning regime. We're just, back to doing linear regression or something like that. And what self-selection bias looks like is, I think the best way to illustrate it is with an example. Let's say you went to the canonical example from the 50s is that you go to a village and everyone in the village is either like a hunter or a fisher. That's the only two jobs available in the village. And you're interested in sort of understanding how do people's features, like their height and their weight and how fast they are, translate into the money that they make from hunting or from fishing. And so, a very natural approach to this would be you go to the village, you survey people, you record their features, then you run a linear regression for hunting, and you run a linear regression for fishing, and then you're done. What people have known for a really long time, though, is that this is a super biased approach. It won't actually tell you how important the different features are for your hunting revenue or your fishing revenue. And the reason is that all of these villagers had the choice of whether they wanted to do hunting or whether they wanted to do fishing. And, assuming they're rational people, they chose the thing that they were better at. So you don't get to see how good this hunter is at fishing, and you don't get to see how good the fisher is at hunting. And the way they partitioned into those two groups is extremely non-random. It's actually based on whichever one would have made them more money. And so there's been a ton of work sort of throughout econometrics, economics, stats on dealing with the self-selection problem. And so with some collaborators at MIT and Berkeley and my advisor Costas, we basically devised an algorithm, an efficient algorithm that could recover from self-selection bias, as we called it, in high dimensions. And so I think that was really cool, both because it's sort of this very distilled model of bias in the data collection process that doesn't have any of the complexity of deep learning and allows you to actually prove stuff.
And how did it work?
So the algorithm itself is quite simple. You can actually just write down a loss function that captures the self-selection mechanism inside of the loss function. And so rather than just doing minimizing your standard loss function, if you minimize this alternative loss function instead, what we showed is that you'll recover the sort of actual ground truth parameters of what matters for hunting and fishing in my example. And then the technical challenges come in proving that you can actually take gradients of this loss function and that doing gradient descent will actually converge and things like that. We assume we're doing linear regression, and we have this very well-defined sort of structural model that we're sampling from. So we assume we have very strong assumptions on what the generative process of the data is. We assume there's no model misspecification or anything like that. We're really just trying to see whether we can recover the parameters underlying this generative process that we've assumed efficiently. And so obviously tons of work to be done along that axis, both along robustness to model misspecification, less restrictive settings, more complex models. But I think it's a really interesting sort of first stab at this question of can we efficiently recover from the data itself that we're collecting from people being biased for whatever reason?
Yeah, because that must be a constant problem.
Yeah, especially in sort of outside of the language model, in sort of more classical machine learning settings where you're a bank or something and you're collecting people's data.
Yeah, and what are the adverse effects of that? Sort of debiasing the data implicitly.
Yeah, so I would say that the biggest adverse effects, the biggest limitations sort of right now are exactly sort of this, you don't really know what's going to happen when the model is misspecified, or when your model of how people are self-selecting is misspecified. So if you're a bank and you assume that someone's going to strategize in this way or strategize in that way, and you try to account for it in your machine learning algorithm, if your conception of how they reported data is wrong, then it's sort of unclear what parameters you're actually going to end up with.
And in this case as well, so it's built into the loss function. And I guess it gets harder and harder to balance the weighting of terms when you have more of them. So, for example, you might do like self-selection bias, and you might do another bias, and then you've got this kind of problem that one might dominate the other.
Yeah, absolutely. I think in general, like this is exactly why we had to study this like very restrictive sort of data generating process, where really your only goal is to recover the true parameters of this data generating process. I think when you get to sort of this machine learning regime, we don't really have a data generating process anymore, or like not one that we can write down at least. And so it becomes a much trickier question of like, okay, we're going to do some accounting for like self-selection or something like that, but we also want to account for this other kind of fairness. We also want to impose this other constraint on whatever outcome we're going to get and things like that. In some sense, like our saving grace in theory land is that what we care about is recovery of parameters. There is a ground truth that we're after, and that's what allows us to actually make progress there. But I think when you go to machine learning, there's no longer this like ground truth parameter that you're searching after, and it makes everything much harder and much murkier.
Amazing. Andrew, this has been so brilliant. How can people find out more about yourself and your lab?
So I will be starting a professorship, not this year, but the next at CMU. So I'll hopefully have a lab website up by the time, I don't know, it won't happen soon, but hopefully by the time I start, there'll be a lab website. You can reach me by email if you're ever curious. It's just my first letter A and my last name, Ilyas, at mit.edu. And my website is just myfullname.com.
That's amazing. So what's going to be your research plan?
I think I'd like to sort of continue working along this ML pipeline direction that I was talking about. I'm really flexible in terms of like where exactly in the pipeline people want to work. But I think things that advance our understanding of, what are the key drivers and things that, make machine learning models behave the way they do in production is really interesting.
Yeah. And are you interested in reaching out to industry?
I think this is a tricky one, I think, with starting out as a professor. I've been advised that maybe you want to do that like during a postdoc and then not do it so much during your first couple of years. I still haven't really decided what I'd like to do. I definitely want to work on problems with practical impact.
Yeah.
Whether that's in the form of industry collaborations or I think something else I'd be really excited about is like collaborating with domain experts in like, for example, like the sciences or in robotics or in sort of these fields that I have less exposure to.
Yeah, it's so interesting because, like in the corporate world, there are loads and loads of, machine learning engineers and architects, and they're building all of these systems out in anger. And it just feels like such a moving target. It's so difficult. So there needs to be this kind of continuous flywheel of, academic research and then boots on the ground actually kind of experimenting with architecture.
Absolutely. Yeah.
Yeah.
I'm really excited for it.
Well, Andrew, it's been an absolute honor and a pleasure. Thank you so much for coming on.
It's been great. Thank you so much.